Okay, so the last two sections of Chapter 9 have to do with properties of solutions that depend on the concentration of solute particles. Of course there are lots of properties like the rates of reactions and the sorts of reactions that can take place in the realm of chemical properties. But what we're looking at now are kind of a special set of physical properties that depend on the concentration of solute particles. These are called colligative properties. And they're interesting because they don't depend on the chemical identity of the solute, only on the number of particles. So, for example, if I were to take 1 mole of C12H22O11, that's table sugar, and I put that into 1 liter of water, then that's going to give me 1 mole of C12H22O11 aqueous. Okay, so that's straightforward enough. Because of the addition of the sugar into that 1 liter of solution, all of its colligative properties will change. And I promise we'll go over those properties. I just want to make one point before we go there. If I take 1 mole of NaCl and put that into 1 liter of water, then I'm going to get 1 mole of Na plus ions and 1 mole of Cl minus ions. And so sugar and sodium plus and Cl minus are very different substances chemically, but they're going to have the same effect on colligative properties. Only in the case of the sodium chloride, that effect will be doubled in strength because you actually produce 2 solute particles for every 1 mole of formula unit that you dissolve. So we need to kind of develop a new type of concentration. If these are both 1 molar solutions, and yet this one is going to have double the effect, then molar concentration is not going to work for us. So for colligative properties, there's one final unit of concentration, and this is molal. And it's kind of hard to say, molal and molality. The molal concentration is a lowercase m, unlike the molar concentration, which is an uppercase m. And the molal concentration is equal to the moles of solute particles. And so that's general. They could be neutral, they could be cations, they could be anions. Whatever is dissolved in your solution, you add up the moles of all the various types of solute particles. In the case of our sodium chloride example, this would be 2 moles of solute particles, 1 mole of sodium, 1 mole of chloride. In the case of our sugar, it would just be the 1 mole of solute particles because the sugar doesn't break apart. And then, here's a little bit funny, we get kilograms of solvent. Not solution, but solvent itself. Moles of solute particles over kilograms of solvent. And kilograms of solvent can be related to moles of solvent through the molar mass. And so what this is disguising is that these colligative properties really depend on a mole fraction, or the fraction of moles that are solvent versus solute. But anyway, we use kilogram of solvent, and water has a density that is very precisely close to 1 gram per liter. So we can sort of cheat a little bit be a little bit lazy and say this is liters of water. 1 liter of water is to at least 3 sig figs 1 kilogram of water, so that works out nicely. This molal concentration is going to be essential for our colligative properties. But before we go do some practice with molality, I want to do that in the context of colligative properties. So we'll do some practice problems a little bit later. Okay, the first colligative property that we want to look at is called vapor pressure lowering. So if you consider, here I've got a beaker, and there's a lot of water molecules that are near the surface. Okay, and vapor pressure is established as some fraction of these water molecules at a given temperature are going to be energetic enough to escape into the headspace above the solution. Okay, but if I don't have pure water, if instead I have some solute dissolved in there, let's say about half of the particles are solute particles, well, that's going to reduce, let's say this one is a solute particle, that's going to reduce the number of water molecules that are at the surface, and it's going to reduce, therefore, the number of them that can escape. Bottom line is, and we're actually not going to deal with this quantitatively, is that when you add solute to a solution, the vapor pressure is depressed, it's lowered. If you go on and take some more chemistry, you would, well, I won't. It's a linear relationship. So if I've got half of my particles are solute particles, the vapor pressure would be cut to half of its original value. Anyway, the fact that the vapor pressure is lowered is actually going to impact another colligative property, which is the boiling point. So let's look at a figure here. This is figure 9.10. And what you see is on the x-axis there's the temperature, and then on the y-axis is the vapor pressure of pure water. As the temperature increases, the vapor pressure increases. That's the red line. And once the temperature reaches 100 degrees Celsius, then the vapor pressure equals atmospheric pressure, or at least standard pressure, 1 atmosphere of pressure. And that is the point at which water will boil. The reason that water boils at lower temperatures here in Cedar City is because our atmospheric pressure is lower. And I believe we talked about this already, how boiling is just what happens when the vapor pressure is equal to the actual barometric pressure. Okay, so that's fine and well. But if you see that blue curve, that is the vapor pressure for water when it's got a concentration of 1 mole per liter of sodium chloride. And you'll notice it's lower. At 100 degrees, pure water has a vapor pressure of about 760 millimeters of mercury. Hang on, I'm going to try something clever. Let's see if this works. No, never mind. I was thinking I could make it kind of transparent so that I could point with my finger. Maybe I could, but I can't figure it out right now. Anyway, so at 100 degrees Celsius, the vapor pressure of pure water is 760 millimeters of mercury. But you'll notice at 100 degrees Celsius, the vapor pressure of our 1 molar sodium chloride solution is closer to 735 millimeters of mercury. It's somewhat lower. And in order to raise the vapor pressure of that salt solution up to standard pressure, 760 millimeters of mercury, you're going to need to increase the temperature to 101 degrees Celsius. Now that's a small difference, but it is a difference. And this phenomenon is called boiling point elevation. The boiling point is elevated because the vapor pressure is depressed. With lower vapor pressures, you need higher temperatures in order to make a substance boil. So let me get that figure out of the way. All right. So the equation we want is that the change in the boiling temperature is going to be equal to is Kb. That is the boiling point elevation constant. And every substance will have its own value for Kb. So Kb for ethanol will be one value, for ether will be another value. For water, I'll just write it over here, Kb for water is equal to 0.51 degrees Celsius per molal. And that Kb will be multiplied by the molal concentration. So let's figure out what is the boiling point of solution if we take 5.0 grams of C12H22O11 and put that into 25 milliliters of water. So that's a fairly high concentration of sugar in water. What will be the boiling point, assuming that we have atmospheric pressure of 760 millimeters of mercury, or the normal boiling point is 100 degrees Celsius? Well, we'll need to figure out the molal concentration, and then we'll plug it into this formula here to get the boiling point elevation. So we'll say 5.0 grams of C12H22O11, and the molecular weight of sugar is 342.3 grams for 1 mole. And hold on a sec. So that's going to be 5.0 divided by 342.3, 342.3. And that's 0.0146 moles, 0.0146 moles. Okay, and then I will divide that by the mass of the water in kilograms. Now I said that 1 liter of water is 1 kilogram, and so 25 milliliters, that's going to be 0.025 kilograms. So this will be 0.025 kilograms. So we'll find the molal concentration. Here, I'll make this just a little bit smaller, and then we can leave it up. We'll make it go all the way down to the bottom. Okay. So we have 0.0146 divided by 0.025. And the molality is 0.584. 0.584 molal. And so here our boiling point elevation is going to be that boiling point elevation constant, 0.51 degrees Celsius per molal times the molality of 0.584 molal. And we'll see that it's actually a pretty modest increase. 0.51 times 0.584, that's 0.298 degrees Celsius. So the boiling point will be elevated by 0.298 degrees Celsius. So the boiling point would be 100.298 degrees Celsius for an atmospheric pressure of 760 millimeters of mercury. Okay. So that's boiling point elevation. There's one very similar colligative property, and that is freezing point depression. So just like the boiling point is elevated, the freezing point of a solution will be lower than the freezing point of the pure solvent. So adding things to solution sort of tends to push both of those phase changes away and expand the range over which the solution remains liquid. So the formula for freezing point depression is exactly the same. It will be the change in the freezing point is going to equal Kf. This is the freezing point depression constant times the molal concentration. And the Kf for water, the freezing point depression constant for water, is equal to 1.86 degrees Celsius per molal. It's equal to a negative 1.86 degrees Celsius per molal because it will lower or depress the freezing point. And so let's do a similar sort of problem. We'll do 5.0 grams, but this time it'll be NaCl. 5.0 grams of sodium chloride in 25 milliliters of water, or as we saw, 0.025 kilograms because water has 1 gram per milliliter. 25 milliliters is 25 grams or 0.025 kilograms. Okay, so just like before, our first step will be to find the molal concentration. We already have the freezing point depression constant, and so we can put them in this formula and find the new freezing point. 5.0 grams of NaCl, and the formula weight of sodium chloride is 58.44 grams for every 1 mole of NaCl. And because this is a salt which breaks apart into 2 ions, we'll add one step here. And that's that 1 mole of NaCl is going to give 2 moles of solute particles. It'll give a sodium and a chloride. Okay, so how many moles of solute particles do we have? Uh, 5 divided by 58.44 times 2. That looks like 0.171 moles. And we're going to divide that by our 0.025 kilograms. So divided by 0.025. Our molal concentration in this case is going to be 6.84 molal. So that's a lot greater than the case for 5 grams of sugar. For 2 reasons. One is that sugar has a larger molar weight, and so there are just fewer moles of sugar. And then the second reason is that the sodium chloride, you get 2 particles for every 1. We can go ahead and put in this formula now, negative 1.86 degrees Celsius per molal times 6.84 molal. We'll say negative 1.86 times our previous answer there. And I get negative 12.7 or negative 13 degrees Celsius. The freezing point of our salt solution is going to be negative 13 degrees, which I think is a fairly impressive amount of freezing point depression. Okay, let's erase this. There's one last colligative property that we need to cover, and it's a very important one, and so it has to do with a process called osmosis. So if I have a membrane separating 2 halves of a beaker, and I fill it with water. Okay, and this membrane allows water particles to pass back and forth, but it does not allow solute like ions. And I dump a bunch of salt into one side, so I'll represent that with a bunch of solute particles. Then water is going to flow through the membrane in order to dilute the solutes on this side as far as it can, attempting to equalize the concentrations on both of these sides of the membrane. And what you'll see is that the water level over here will rise and the water level over here will decrease as water flows into that side and tries to make it equalize the pressures. Usually people will draw a U-pipe, and that's what I should have done. Makes maybe a little bit more sense. So there's my selectively permeable membrane, and here's where I've got the solute particles. There we go. The U-pipe is a bit better. Okay. So there is going to be a column of water on that side that is defying gravity and raising up against that pull of gravity. And so there's going to be a water pressure that is generated on this right side of the U-pipe. And that pressure is what we call osmotic pressure. The process of water percolating through the selectively permeable membrane is osmosis, and the pressure that is generated by that percolation is called osmotic pressure. And we represent osmotic pressure with a big uppercase pi, the Greek letter pi. There's 2 different ways to think about osmotic pressure. One of them is that it's the pressure generated by the column of water on this side. You could also think of it as the pressure that you would need to apply if you wanted to force the water back over to the other side. So you may have heard of reverse osmosis purified water. That's where you take salty water and you put it in an apparatus like this with a selectively permeable membrane, and then you apply strong pressure to force the water through the membrane, and you collect pure, clean water on the other side. So I think reverse osmosis is a common enough process that you've probably heard of it. And osmotic pressure is the amount of pressure that your reverse osmosis apparatus is going to have to apply in order to get pure water out the other side. Okay, so how can we calculate the pressure that is required? There is a formula. Pi is equal to nRT over V. Now this looks exactly like the ideal gas law. PV equals nRT. If you just change the P to a pi, which is just as easy as booking a flight to Greece and changing the Roman letter for a Greek one, and then take the V and divide it over to the other side, then you've got the osmotic pressure equation. To me, it's really remarkable that osmotic pressure actually follows this formula. It's really kind of bizarre, but it does. So osmotic pressure follows basically the ideal gas law, where N here is moles of solute particles. V is the volume of solution. R is the gas constant, and in this case we want the 0.08206 liters atmospheres per mole Kelvin. T is the temperature in Kelvin. And we can rewrite this, recognizing that number of moles of solute particles over the volume, well, that is simply the molar concentration of solute particles times RT. So let's look at a practice problem. So let's find the osmotic pressure for 5.0 grams of sodium chloride in 25 milliliters of solution. Right, that's what we were looking at earlier for our freezing point depression constant. And if I look back at my numbers, the 5 grams of sodium chloride divided by 58.44 grams per mole times 2, because we have 2 moles of solute particles, and osmotic pressure is a colligative property that depends on the number of particles regardless of their identity, then that's going to be 0.1711 moles. 0.1711 moles. We'll divide that by the volume, 0.025 liters, and we'll multiply it by the gas constant, 0.08206 liters atmospheres per mole Kelvin, and the temperature, and I failed to give you a temperature, but let's just say 298 Kelvin. That is room temperature. So let's figure this out. We're going to have Oh, can you see that? Sorry, you can't see that. Let me pull that up. Okay, so we're going to have 0.1711 divided by 0.025 times 0.08206 times 298. And our osmotic pressure is going to be 167 atmospheres. Now, if that seems like an incredible pressure, you're right. Osmotic pressures can be extremely large, but there's nothing wrong. We haven't done anything incorrectly. That is indeed the osmotic pressure. So if you had a salt solution that was 5 grams of sodium chloride in 25 milliliters of solution, and you wanted to extract pure water through a reverse osmosis apparatus, you would need to apply that incredibly high pressure in order to get the water out. That's why reverse osmosis, as a method for purifying something really salty like seawater, for example, is actually not very efficient. It takes an awful lot of energy and expensive machinery to consistently, day in and day out, apply that high pressure and generate a usable amount of water. So there's one last quick application to osmosis. Sorry, one moment. Get rid of the console and put up the figure. So this here is there, now you can see my face. These are images of red blood cells under different conditions. If you're all wanting to be nurses, then you'll probably be giving patients intravenous solutions. And even if you're just giving them water to keep them hydrated and there's no medicine in the IV, you shouldn't give them pure water. You might think, oh, good distilled, purified water is the best thing. Well, actually, no, that would be very bad for your patient. So if you look at these red blood cells, you can see that the ones in A are healthy. They have been placed in a solution whose salinity, or in other words, whose molal concentration of ions is equal to that of normal human blood. If you look at number B, those red blood cells appear to be swollen. The little dip or depression is not nearly as pronounced. They look a little bit bloated. So that is a red blood cell that's been placed in water that is too pure. And you know, it may not look that bad under that microscope image, but the osmotic pressures can become so high that the red blood cells will rupture and it will kill the blood cells. And then if you look at C, it's a little bit hard to understand what's going on with picture C, but those are red blood cells that have been placed in a very salty solution. And that salty solution is leaching all of the water out of the blood cell. And it's kind of like getting sucked inward, and I believe all of that spikiness is the various organelles and things. It's like how a cow that hasn't had enough to eat is going to show its spiky bones and shoulders and ribs sticking out. Well, this is a red blood cell that's lost all of its water, and so its spiky organelles are sticking out. Don't quote me on that. I'm not a microbiologist, but anyway. So, oh shoot, I just forgot the terms for this. Oh, good, I got them in my notes. So a hypertonic solution has too much salt. That will result in picture C. A solution with not enough salt is called hypotonic, and it will cause water to rush into the blood cells. The blood cells themselves have a lot of salt, and so water will rush in and it will swell them or even burst them. And so that's a hypotonic. And then isotonic is what you're shooting for, a solution that's equal to the salinity of normal human blood. That will result in healthy blood cells. Okay, so that's it for Chapter 9, and I'll see you again on Thursday.